Okay, we can start now. Do you hear me, David and Maria?
Yes.
Yes,
I hear you quite well. Yeah.
Yeah, perfect.
Yes.
So welcome to the defense of Qingchuan ZHU on low-cost sensor for monitoring stormwater source control measures. So I'm going to chair this committee. I'm Jean-Luc from INSA. So I'm going to briefly introduce the member of the committee. So we have Maria Vikander online. Yeah, right. Yeah, online. From the University of Technology, Luleå, in Sweden. And we have also David Zhu from the University of Alberta in Canada. And we have Pierre-Antoine Versini, École des Ponts, Paris. We have Flora Branger, INRAE. And we have the co-supervisors of the thesis, Frédéric Cherqui and Jean-Luc Bertrand-Krajewski. So you have 45 minutes for your presentation. So the floor is yours.
Thank you. Good morning, dear committee and dear audience. I'm Qingchuan, and today I'm very happy to share you my work running last 3 years about the low-cost sensors for monitoring stormwater source control mirrors. You can see, during most of my work, I compare low-cost sensors here with nearby default sensor, and I have many interesting results to share with you. About the plan of today's presentation. Firstly, I want to discuss why do we need low-cost monitoring, and then I do a literature review about how do low-cost sensors perform in the literature. Next step, I want to tell you how to assess low-cost sensors performance in my PhD work, and then the test results about weather sensors, rain gauges, and water level sensor and monitoring station are discussed. In the last part, I give the general findings and the future of monitoring low-cost. First part, why do we need low-cost monitoring? During the past few years, stormwater source control mirrors are building around the world. For example, like this picture of the green roof. And these stormwater source control mirrors need operation and maintenance. In the past, we always wait this structure to fail and we repair it. But now, because they have green part, so we need to operate and maintenance them. So we need to go to active management to them. So how to shift to active management? We need to increase monitoring. But because the resource limits, we do not have so much time and money to take care of them. And open source company give us opportunity to build our own system to manage this building, this infrastructure. So we can do low-cost monitoring to save money and time. And why do we need to test the low-cost sensors? I think low-cost monitoring have 3 parts. First part is the low-cost sensors, and the next part is open source hardware, and the third part is the low-power wide area network to help users to get the data online. When we discuss open source hardware, we have a professional supplier like Arduino, and about the low-power wide area network, we have Loha and Sigfox to guarantee their system performance. But when we check the low-cost sensors parts, low-cost sensors do not have clear definition, do not have brand. Most of them do not have brand and do not have known supplier, and they have very low quality data sheets. So local sensors need more tests. And then I do a literature review to find out how others do to local sensors. And in this literature review, I define that local cost sensor should be a sensor that its price is at least 10 times lower than the traditional instruments, and or this sensor already used in a low-cost monetary unit. In the literature review, 3 categories, 43 sensors, and 202 papers are reviewed. And this review already published in the Water Science and Technology a few weeks ago. About the categories to assess sensors performance, I refer to the international standard and academic recommendation. I choose the following criteria to check the sensor performance. About the trueness criteria, this criteria is used to check how the tested sensor close to the reference sensor. And about the repeatability criteria, it means that this sensor in the same condition, its output is same or not. About the reproducibility criteria, this is to tell that when we have 2 same mode sensor, do their output same in the same condition or not? About the resolution, this is a criteria to tell that when the mirrored quantity changes a little, the small is the indicator output of the sensor give. And about the response time criteria, this is used to tell that when the tested quantity changes a little, how long time the sensor needs to respond. About the sensitivity to environment, maintenance needs, and the longevity, these 3 criteria is used to tell us the sensor longevity, about how much we need to cost to keep their performance. And my main findings about this criteria is this. About the first 3 criteria, accuracy criteria, I find that both local sensor manufacturers and local sensor users themselves do not do authentic assessment. About the resolution criteria, the situation is same. And about the response time criteria, the reviewed sensors all have similar to reference sensor, and these results are documented in the manuscripts. About the last 3 performance criteria, we cannot give a quantitative result because these 3 criteria are highly influenced by sensor location, local climate, and maintenance frequency. About in this literature review, 3 different kind of sensors are reviewed. About first one is the water sensors, include air humidity sensor, wind speed sensor, salinity sensor, and rainfall sensor. And the next is water quality sensor, quantity sensor, include water level, water flow, and soil moisture. And the last part is the water quality sensor, include pH, conductivity, turbidity, the nutrient sensor. And my main findings is this. About the first 2 categories, weather and water quantity, I find many local sensors are used, and but they are lack of authentic assessment. About the water quality sensor, because these sensors need more frequency maintenance, so I do not think there is a real low-cost solution to test to mirror water quality now. After the context check and the literature review, I have these questions on my PhD work. First one, I want to answer: is low cost monitoring a promising error diagram? And then I want to give that what low cost sensor is possible to be used to support research or operation to stormwater source control mirrors. And then how to assess the authenticity of the measurement output of local sensors. And then how to assess the whole performance of the low-cost monitoring unit In the next part, can we help others? Can we provide a repeatable local simulation system design? Others can just repeat our design. And the last part, last question, can others strictly refer to our uncertainty assessment results? And in this part, I want to take the low-cost wind speed sensor as an example to discuss how to assess local sensor performance in this PhD work. In my work, I compare local sensors with nearby reference sensor. So ordinary least squares equation is used to correlate sensors output. For example, take onimeters comparison as an example. You can see this figure. The x-axis is the reference wind speed sensor output in meter per second, and the y-axis is the low-cost sensor output in meter per second. And every minute output can give a data point in blue, and after 1 year, there are many data points. So ordinary least squares equation is used and give this response equation. And if the local sensor and the reverse sensor is very same, we can get a perfect response, y equal to x. But here, local sensor have an offset error 0.1 meter per second, and it has a sensitivity error 0.9, and this value do not have limits. And then how to understand sensor accuracy? Because in my work, I face a problem. I cannot check the reference sensor, and because so we need to choose to trust the reference sensor. But when I check the data sheet of the reference sensor, many sensor, almost all sensor manufacturers give a parameter accuracy, and we do not know what accuracy means. For example, in the data sheet of the reference onimeter, it just says that this sensor have accuracy minus plus 0.5 meter per second. And when I check the academic recommendation of alternative assessments, I find that, for example, if we do if in the unreal perfect situation, we do many tests to test one single physical value, we can get measurements. We can get a measurement distribution probability distribution, and then we can by distribution we can get that the coverage interval, for example, 0.5 to 1.5, we can choose that at a given level of probability, for example, 95%, the true value of the measurement physical quantity will have 95% possibility to fall in this range, in this coverage interval. And the half of the coverage interval is the enlarged uncertainty at a given level of probability. So I assume that the accuracy parameter given by manufacturer is the enlarged uncertainty at 94% level of probability. And then we can compare the sensors performance in a new way. And for example, I assume that at one time stamp, when local sensor and reverse sensor output coverage intervals have an overlap, local sensor output is assumed to be correct. For example, when still use wind speed sensor as an example, at this time, at this minute, the reference wind speed sensor have output 1 meter per second in blue, and the local sensor output wind speed 1.75 meter per second in red. And at this time, these two sensors output different values. But if we consider the large identity and the charge interval, for example, the reference sensor have one electricity 0.5 meter per second. So in fact, at this time, the reference sensor give a range, give a current interval. And if we also assume that the local sensor have an electricity 0.5 meter per second, so this local sensor also give a range. So even though these two values, 1 and 1.75, are different, but these two ranges have an overlap. And I assume that at this means the local sensor output is current. So it's obvious that if we change the local sensor in large assembly, we will increase the correct of we will make most of the local sensor output to be correct. So if we compare multiple data sets in a time series, we will get a current rate. For example, for the low cost anemometer, when the electricity 0.24 meter per second, the current rate of the more than 1 year data 95%. So in the last part, I use anemometer sensor as an example to give the what I do to assess sensor performance. So in this part, I will discuss my weather sensor test and the weather sensor test on this. And I design a system to test the weather sensors. In this system, I test the wind direction sensor, and the speed sensor, and the rain gauge in one kit, and two different air temperature and humidity sensor. And the pyranometer, a light sensor is tested. All these sensors is connected to a main controller to get data, and this main controller is Arduino Nano. And this main controller is connected to a data logger laptop to save data. And this laptop is remote controlled to get data conveniently. And in my test on the green room platform of INSA, reference weather station and low-cost weather station is installed nearby. And here is the sensors and sensor name of reference of a low-cost weather station. You can see the rainbow sensor uses connect the low-cost rainbow sensor is a tipping back rainbow. So it uses connect of the read switch to output value, and the wind speed sensor also use the connect of read switch inside it to output. And the wind direction sensor uses the position-based resistance to give wind direction output, and it can only output 8 different wind direction. And the solar radiation sensor, it has a photodiode element to convert heat to watt. And the air temperature and humidity sensor both are capacitance humidity sensor. And the light sensor SI is in the box, and it also has a photodiode element to get the environment output. And this is the operation details of the whole test. You can see for most of the time, the rain gauge, anemometer, and the pyranometer test for a long time. And at the end, the anemo stop because I make a mistake in the maintenance. I disconnect it. And the PME sensor just test for the first 3 months because it's malfunction. I will show later. And the digital sensor here also because of maintenance mistake. And the light sensor only test for the last 3 months. And the whole test lasts for 60 months. And the most reasons of data log interrupts is because of the laptop problem and maintenance and the laptop software failure. Because there are many sensors tested, but the longevity of this precision is limited. So I just discuss most interesting results, and all the results are given in the manuscript about the low-cost feedback ring gauge. Now it is as a part of the verification kit, and I find that it's in this solution is not stable. For example, this is a one-day result of the sensor of sensor output. This blue line is the reference stimulus ring gauge output, and this red line is the reference wave ring gauge output. You can see in this one day, there is only a little ripple event at night. But when I check the local stimulus ring output this day, you can see local stimulus ring gauge out and about put many big tips in this day. And I think this is because that today, in this day, the wind speed is very high. For example, this is the output of the local meter. And I think when the wind speed is more than around 10 meters per second, its wind will shake the ring gauge. So the ring gauge outputs big tips. I conclude that feedback ring gauge in this installation is easy to be disturbed by wind, even though this installation is the recombination of the weather station kit supplier. About the local air temperature humidity sensor BME, why I just tested it for the first 3 months, because after 2 months installation, I find it is malfunctioning. It is a malfunction. For example, this is the several days results. The reference output is in red, and its lower limit and the higher limit is getting from plus or minus in large density. But the local sensor BME sensor output is in green, and you can see when the relative humidity is low, the two reference and the test sensor output similar. But the humidity, when the humidity is high, the BME sensor output too high. So I just give up test more BME sensor. About the another air humidity sensor, you can see this sensor is different from the BME sensor. It have a house. And after in 1 year test, this sensor output a very similar temperature as the reference sensor, and it only has a little offset error. And about its humidity output, this sensor also has a little offset error. And when I use the inverse function of this shift to correct sensor outputs, I calculate that when the correct sensor output bandwidth rate is 95%, the inadjacency of BME sensor output is 2.3 degree and 5.7 rate humidity. And this is the key findings of all the test weather sensors. Firstly, as discussed in part 3, the anemometer output is stable during 1 year test, so it's possible to be used in research and operation. And about the wind direction sensor, even though its output is stable, but it can only output 8 different wind direction, so we have a reserved opinion about BME because it's a poor longevity. We do not recommend to use this model of BME. And about the DT22 sensor, it is also possible to use about one tested parameter because this sensor outputs very different, very higher than the reference. So we have a reserve opinion about its performance. So, and about the light sensor, because this one is very cheap, but you need to build a house for it. So we also have a reserve function opinion to this sensor. Because the rain gauge is very important to rainfall monitoring. So I built a single rain gauge system to test the rain gauges and test the whole system performance. This is the hardware of the final design of the rainfall monitor station. This station has one shipping plug rain gauge connector, one optical rain gauge connector. The main controller of this system is MKR WAN, and an SD card model is used to save data locally. And a real-time clock model is used to get to output correct timestamp. This is also important to monitoring. And the antenna is used to send the data online through low power network. And a power management board is used to power the whole system by solar panel and a battery or by the outer power supply. And a big battery used to power the whole system. This is the last version system, and during 1 year, we suffer from 5 versions of hardware improvements and 16 versions of software improvements. And this is the final test setup of rain gauge system. Beside the low-cost system, there is a referred rain gauge. And after the laboratory calibration and after comparing to other systems on the green platform, we are sure that this referred rain gauge has a resolution 0.23 millimeter per tip. And 3 same local default rain gauge are tested, but when we refer to its data sheet, we cannot know its resolution. And 3 same stations are built to connect to each default rain gauge and optical rain gauge, and they are put in a waterproof box. And 3 optical rain gauge is tested. This optical rain gauge is based on infrared light beam change. When here is a stormwater drop on the surface of the sensor, the infrared light beam will change, and the sensor will detect this change. And this final test lasts for 4 months in winter. About the test results of optical rain gauge, you can see this this is a half month test. The red line is the reflective target range output, and the green line is the low cost optical rain gauge number 1 output. Because this test is in winter, so at the beginning it seems correspond, and at this period there is a rainfall unit. So because the optical rain gauge cannot respond to snowfall units, so it's a little different. But even though when we check the coverage interval of 2 sensor outputs, there is still an overlap. And this the coverage interval of reference default rain gauge is according to that its enlarged uncertainty is 10%. And optical rain gauge number 2 has similar outputs. But when I check the output of optical rain gauge number 3, even though I try to fix it, but you can see its output is very lower than the reference. And the 2 coverage interval has no overlap. So I conclude that the low cost optical rain gauge has poor reproducibility. Because the test of the weather station, I install the optical rain gauge in a more stable in a more stable way, and this is its result. During 1 month test, reverse gathering gauge outputs more tips of about 3 times tips than the local tip gathering gauge, and I also check the regression results of every 5 minutes output, and I conclude that at this original setup, the local tip gathering gauge without lubrication and with original funnel has a resolution about 0.6 millimeter per tip, but this resolution is too big to use in the stormwater monitoring. So we use 3D print to build an additional funnel to increase the rain gauge catchment area in 3 times to decrease the resolution, and the result seems good. When increases the funnel area 3 times, the resolution decreases 3 times by tips check and by regression results. However, during the calibration in depth, I find that this sensor has a resolution 0.1 millimeter per tip. This is very strange, and I find that this is because that in the lab, I always drop the water directly in the hole of the Qingchuan rain gauge, and in fact, in the field, the rainwater can drop anywhere of the funnel, and because the funnel area is not perfect and its surface is not smooth, the raindrop drops will fix on the funnel, and the water cannot drop in the bucket directly. So, according to this test, we design another additional funnel. This time, this funnel has a perfect shape and it is well lubricated by softening. And during the several days test, when the reference peak, when the low cost Qingchuan rain gauge has a resolution 0.1 millimeter per tip, since the low cost output and the reference output are very similar in this and this ripple event, but in this little unknown thing, reverse rain gauge output 4 unknown tips, and we will check more data to check all the sensor performance. And we conclude that local rain gauge resolution with concealed shape, triple area and large funnel, and well lubrication, it will have 0.1 millimeter per tip. About the main findings of tested rain gauge and the system. Firstly, the optical rain gauge, even though it is very well in shape, it is a stable sensor, but it have too high sensor to sensor variance. About the tipping boundary rain gauge, I test 6 mode sensor, and I find that this bucket part is stable during test, but its funnel is too small to have big resolution, too shallow to catch rainfall water, and it's unsmoothly. So user should not try the sensor without modified stormwater catchment funnel. About my DIY station, after 1 year improvement, I get that its local data storage function meets the design objective. But when we check the online data, because the unstable of the local one network itself, sometimes we will lose data online. So this DIY station should always have a local data storage, and this system is ready to share to others. And I already uploaded the design in GitHub. About the water, the 6th part is about the water level sensor tests and the monitoring station. This time, we want to monitor the water level of a free surface, and the reinforcement station have a price around 200 hosts. And now we want to build a more low-cost system. This system should be small and should be less than 100 hosts, and it only rely on the remote access to data. And it should have reduced power consumption because there is no outer power supply, and it only relies on the solar panel, and it should reduce site visits. After compared to ultrasonic water level sensor and capacitance water level sensor, a pressure sensor YP is chosen because it is stainless steel house, it is less sensitive to environment, and it has low maintenance needs and frequency. And this is the water level system design. Here is the pressure sensor connector, and here is the solar panel connector. 3A battery is used to power the whole system. Here is the read switch because during maintenance, usually user should open the box to check the system. But if we at the read switch decided one can start the measurement immediately by magnet, so it's maybe no need to open the box anymore. And here is the sensor signal converter because the pressure water level sensor can only output current signal. So a resistance is used to convert the current to watt, and the converter is used to mirror the watt more accuracy. And antenna is used to upload data through sigfox. And a power management board module is used to power the sensor. And this time we try another main controller because this controller can use both sigfox and the low-power network. But unfortunately, the supplier of this main controller is bankrupt. And a mode, this red module is used to wake up the system at 40 minutes. So during this 40 minutes, the whole system will not consume any power. So this system will have very low power consumption. And in lab, we also have a system to calibrate the pressure sensor automatically. You can see upper part is a DHT2 sensor to get the lab test environment parameter, and pressure sensor and full pressure sensor, reverse pressure sensor, and reverse local pressure sensor are installed in below to mirror water level and to mirror the water level of the tube. And a pump is used to increase or decrease the water level automatically. And this whole system is a very great automatic system. And this is the laboratory test results. You can see the x-axis is the reverse sensor output water level in meters, and the y-axis is the low cost output in watts. So this output, low cost output is very linear, and this equation is the calibration equation of the low cost water level sensor. And when you use this calibration equation to compare the sensor performance, you can see the low cost, the reference sensor has an energy density about 2 centimeter, and when in this energy density of the reference sensor, we cannot give a reasonable energy density of the reference sensor of the local sensor because the energy density is very small. So we can only conclude that the tested local sensor has a comparable performance as the reference sensor, and even though its price is 50 less than the reference. And in this whole system, I tested in field for more than 1 year. You can see the low cost water level station is installed in a pit, and a metallic grate is used to protect the system. But this metallic grate also influences the sigfox signal. And little solar panel is used to power the monitoring station. And this is the 1 year result of the sensor output. And you can see local sensor output is in green pot and green point in meter. Even though here is a reference sensor in field also, but because we do not calibrate the reference sensor and the reference sensor intensity according to its datasheets is very big. So we give up to compare the low cost and the reference sensor performance in field. And we just focus on the whole system performance. For example, can the whole system continuously report water level in time? But unfortunately, you can see in this 1 year, we do not have any data because we do not update the screen in time. And the most data loss and the longest time, we do not have data for 5 hours sometime. So we conclude that it's not feasible to rely on online data only. About all the test system, we concluded that this low-cost pressure delivery sensor is a good sensor. During lab tests and during in-field tests, it do not send any outlier, but because this sensor can only output current signal, so users need to build a signal processing circuit by themselves. And because in fact you build parts of the sensor, so the calibration is very important and it should be due per periodic because this sensor may influenced by water temperature, for example. About our DIY station, because this station only rely on the online data, so I find that the data, the signal quality of the, for example, sigbox are not great. So the data quality is not very good. So the local data storage is strongly recommended. And about the general findings and the future of the low cost monitoring. For the 6 questions, I answer that low cost monitoring is a promising paradigm. And the following sensors are possible to support work. First one is the wind speed sensor, and during 1 year in field tests, its elasticity is 0.24 meter per second. Because the datasheet of this sensor do not give any parameter about accuracy. So maybe others can use our elasticity value we give. And LVD sensor also very stable during 1 year in field tests, but the ring gauge sensor should build additional funnel design. And its elasticity is also dependent on the funnel design. For the pressure sensor, users should also test elasticity by themselves because users create part of the sensor by themselves. And how to assess the sensor performance? I think one can assume that in the sensor datasheet, accuracy equal to elasticity and calculate the sensor output frequency rate to assess sensor performance. And about the whole low-cost monitor unit performance, I think the most important part is this unit should continuously record sensor output on time. So you should always use local data storage. And all my system design have been shared online. And maybe others can refer to our elasticity even about the future of those monitoring. And this is all the system I have built, and this system can send data online, even though not in a very good quality. And this is only a single node of the inside campus. Maybe in the future there will be many other nodes. All these nodes will build a low-cost monitoring network. So about when we have many stations, how to do the systemic calibration, how to do a better bicycle deployment. For example, choose the location of the monitoring points and how to real-time control the whole network. The future of local monitoring also have many questions. That's all. Thank you for your attention.